Okay, we're going to get started again here. So let's take a look at 21. Byproduct ammonia is recovered from the solvate process by the reaction. Okay, so we have calcium hydroxide, ammonium chloride. When I look at this, this is an AB plus CD. Looks like a metathesis reaction. And so calcium ions with chloride ions. Okay, calcium ions with chloride. We're trying different combinations. And then ammonium with hydroxide. But I don't see ammonium with hydroxide here. And the reason we don't see ammonium with hydroxide is ammonium hydroxide is unstable. It's like ammonium nitrate. When you have ammonium nitrate, you have ammonium, which is a fuel, and nitrate, which is the oxidizer. So you have this would be like the caged gazelle kind of thing I was talking about with dynamite here. Ammonium is a good fuel, nitrate's a good oxidizer. So this is an unstable compound. Well, the same thing, but in terms of acid base. Fortunately, this doesn't result in a huge explosion. Ammonium nitrate is going to result in a gigantic explosion. Ammonium hydroxide has the potential to result in a pressure explosion. It just builds up pressure because gas is generated here. And so we get like a pressure explosion, not a chemical explosion. So there's more of a physical explosion, but if there's no big container, then it's probably okay. This is acid-base. Acid-base reactions are usually a lot less energetic than redox because nothing happens in the oxidation state. There's not this Dr. Jekyll and Mr. Hyde thing going on with, acid-base. And so what's happening is we have this metathesis going on. And the metathesis, when we look at the metathesis that's happening, it's calcium hydroxide. Calcium hydroxide, most hydroxides are insoluble except group 1, ammonium, calcium, strontium, barium. So calcium is one of those exceptions here. And so this is what it's aqueous. And then all ammonium salts are soluble. So we have 2 ammonium chlorides here. Here. Now in metathesis, we just switch the ions to C. Does calcium prefer chloride over hydroxide? And so it doesn't really, because this is also soluble. If it were insoluble like a precipitate, then yeah, for sure. But that's okay. All we need is one driving force. How about ammonium? Does ammonium prefer hydroxide over chloride? And the answer is yes. Ammonium prefers hydroxide over chloride. How come? Because ammonium hydroxide isn't going to decompose immediately. And so ammonium is an acid, hydroxide is a base, and then we're going to have proton transfer. And so we're going to end up with 2 ammonias. Each ammonium loses. And then if hydroxide takes a proton, it forms water like this. And so we have gas formation here. It's one of the things that can happen. Also, it's, when we look at the ammonium hydroxide itself, if I have ammonium ions, ammonium hydroxide is a strong electrolyte. Strong electrolytes break apart in solution. So I have ammonium ions and hydroxide. So ammonium ions and hydroxide come together. And this is going to form ammonia and water. And so when we analyze this, this is a, Bronsted acid base. When we analyze this, this is our acid, this is our base. Now, if we went backwards, we're looking at which way is downhill. So if we go backwards here, then what would ammonia's role be? Ammonia would be taking the proton. And so this would be the base going backwards. This would be the acid. Water would be losing the proton here. And then we look at the 2 bases, like hydroxide versus ammonia. Well, hydroxide is a strong base. Ammonia is a weak base. So this is strong, this is weak. Let me compare ammonium and water. Ammonium is a stronger acid than water. Water we don't really think of as being an acid. And so this is not W, this should be S. This is a stronger acid, this is a weaker acid. And so this is the decomposition of ammonium hydroxide. We form ammonium hydroxide aqueous, which consists of ammonium ions and hydroxide ions, and those react together to form ammonia and water. And so this is favorable. And so this is why they get the ammonia here, and the water here, H2O is liquid. This should be aqueous. This is aqueous. And so this is an example of metathesis this is the metathesis, followed by a Bronsted acid base, decomposition of ammonium hydroxide. And so it's actually 2 reactions going on here. But overall, this would be a metathesis because it's metathesis because of this calcium hydroxide and ammonium chloride metathesis. How many grams of calcium chloride can be produced along with 62 grams of ammonia? So if we produce 62 grams of product here, ammonia, then we go grams of ammonia to moles of ammonia, moles of ammonia to moles of calcium chloride, which is also a product, and moles to grams. So this is just a standard grams of A to moles, moles of A to moles of B, moles of B to grams of B, where A is ammonia, B is calcium chloride. It's just your standard problem. How many grams of sodium hydroxide are needed to neutralize completely 32.6 grams of phosphoric acid? Now your book calls this a neutralization reaction. I don't call it a neutralization reaction. I call it just a metathesis reaction. You know, it's a metathesis reaction because of this. Let's take phosphoric acid, H3PO4, and then sodium hydroxide, NaOH. And what do we form? It's a metathesis. So we're going to form hydrogen ions with hydroxide. Hydrogen ions with hydroxide just forms water. And then we form sodium ions with phosphate. Well, sodium ions are +1, phosphate's a -3. So we're going to need 3 sodiums. So this is going to go Na3PO4. And this is going to be, we need 3 sodiums here. So we'll put 3 sodium hydroxides here. And we have 3 hydroxides and 3 hydrogen ions. That's going to form 3 waters here. And so this would be balanced. Acids like phosphoric acid are soluble. That's 8 cubed. So this is H3PO4. Sodium salts are soluble, 8 cubed. H2O is a liquid. Sodium salts are soluble, 8 cubed. So what's the driving force for this? The driving force for this is we're going from a stronger acid, phosphoric acid, to a weaker acid. The weaker acid here is going to be water, weaker acid. And so this will be our driving force, stronger acid, weaker acid. And note what's happening here. This is called a neutralization reaction because we're neutralizing phosphoric acid and making water here. We don't always make water in neutralization reactions. In this particular one we do. But, you know, if I said neutralization reactions, you might think, well, how do you do a neutralization reaction? Well, this is just a metathesis reaction. And so we just do it the standard way. We just completely react everything to get the products here. So how many grams of sodium hydroxide do we need? So if we had 32.6 grams of the acid, pure acid, you know, these are aqueous. This is not 32.6 grams of mixture. If this were 32.6 grams of mixture, then it would be a more complex problem because we got to go from grams of mixture to grams of pure acid to moles of pure acid, you know. But this is just grams of pure acid. So we'll go grams of pure acid to moles of acid to moles of sodium hydroxide we call base. And this is acid being neutralized by base. Moles of base to grams of base. In other words, this is a standard stoichiometry problem. Grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. We need the balanced chemical equation here. Metathesis reaction. This could also be a Bronsted acid base, but it would be 3 successive Bronsted acid base reactions. So if it fits a metathesis problem, then just do metathesis. Make your life simpler. Solid ammonium chloride decomposes to form ammonia and hydrogen chloride gas. Now, this is not favorable. This has to be heated. And so you could say upon heating, you know, because we're going from a weaker acid to a stronger acid in this particular case. You know, hydrogen chloride is HCl, it's a strong acid, compared to ammonium ions, which are weak. But this is not one of the blue problems, I'm going to skip it. What mass of magnesium hydroxide will precipitate if 2.09 grams of potassium hydroxide is added to a magnesium nitrate solution? Okay, so They're telling us what's going to precipitate, but we could have figured it out anyway because we're taking potassium hydroxide, which is KOH. I probably wouldn't have told you. Taking KOH and adding it to magnesium nitrate. Magnesium nitrate, magnesium is a 2+, whereas nitrate's a 1-, so we need 2 of these to balance out the charge. And so this, we could have figured out the product because this is just a double replacement, AB plus CD. So we're going to get potassium ions with nitrate. Well, potassium ions with nitrate is just KNO3. I don't care that there's 2 here. I want the formula correct here. And then I'll balance everything at the end. And then I want magnesium with hydroxide. Magnesium needs 2 hydroxides because each hydroxide is a -1. So we have that. I don't care that there's only 1 hydroxide here because we balance it at the end. I just need the correct formula here and here. KNO3 is always this. Magnesium hydroxide is always this. All right, now we can balance this, but we need driving force. Well, they told us what the driving force is. Hydroxides. Hydroxides are all insoluble except for group 1, ammonium, calcium, strontium, barium. Magnesium is not one of the exceptions, so that precipitates here. Potassium salts are all soluble. That's AQ. This is aqueous. How do I know? It's solution. Whenever we have a solution, it's going to be aqueous in this class. So now let's balance it. So we need 2 hydroxides, so that's an easy fix. Change the coefficient to 2 here. If we got 2 hydroxides, we got 2 potassiums, so we'll have to change that to 2 there. Anyway, this is grams of potassium hydroxide. So grams of potassium hydroxide, we'll go to the moles of potassium hydroxide. The moles of potassium hydroxide to moles of magnesium hydroxide. You know, we don't care about the magnesium nitrate. We'll just skip over that. So we'll go to moles of potassium hydroxide all the way over here to moles of magnesium hydroxide. And then from moles of magnesium hydroxide, we'll go to grams of magnesium hydroxide. And that should be it there. Let's see, what I have to do here is this. Let's do this. Let's do a challenge problem here. Those are some of the basic problems. We'll come back to the basic problems, but I have to take a little break here. We can break you up into groups. All right. Why don't you guys try number 77 here? Number 77. Remember what I said, we're going for the core. And so let me break you up into groups here. Just 1 second. Okay, I'll be ready in just 1 minute. I'm gonna okay, yeah, let me know if you have any suggestion, if you want to, in a particular group. But let's see, breakout rooms manually. How many? We have 16 people today. Okay. These are kind of random. But now, remember what a core is, you know, the grams of eta, that kind of thing. And then try this one, number 77, which is like a advanced variation of that. And I'll be back. and a little bit. Okay, I'm going to pause the recording now, though. Zoom. Did you guys figure it out? Yeah, good. Kazra, anybody not figure it out? Okay, good. Let's take a quick look at it then. A phosphate rock, this is going to be a mixture. You know, rocks are mixtures of minerals. Minerals are compounds. Yields 79.4% of the compound calcium phosphate. The raw material used in preparing calcium, this is dihydrogen phosphate, a fertilizer known as superphosphate. The rock is made to react with sulfuric acid according to the equation. So if there's calcium phosphate, this rock contains 79.4% of this mineral, which is calcium phosphate, which is just the compound. And it contains other stuff. And so the other stuff's got to be inert, you know, it's unreactive with sulfuric acid. And so the sulfuric acid, normally when we do something like this, you know, it depends on the conditions we do it with. Because if I looked at this particular reaction, I would say this reaction is a metathesis reaction, but I would have predicted different products here than what they predicted. The products I would have predicted are like this. I would have said, okay, this is just an AB plus CD type reaction. So we have calcium phosphate. You know, calcium is a 2+, phosphate's a 3-. And so to balance it, we'll need 3 calciums and 2 phosphates. Phosphates are insoluble. You know, these are some part of this rock. And then we have sulfuric acid here, H2SO4. And so I see AB plus CD. And so I would have predicted, and this is the way you should predict it too, we're going to have calcium with sulfate. Well, calcium with sulfate is, you know, calcium is a 2+, sulfate's a 2-, so it's just going to be CaSO4. And then we're going to have hydrogen ions with phosphate. When we have hydrogen ions with phosphate, you know, hydrogen is a +1, so we'll need 3 of those for every phosphate, which is a -3. So I would have predicted we form calcium sulfate and phosphoric acid. This is what we call complete reaction here. And so when you do this, when we do metathesis, we go for complete reaction. If we want partial reaction, then what we have to do is we have to adjust the conditions to get partial reaction. And so in this case, they're only partially reacting. You know, phosphate will want 3 hydrogens, so they only give it 2. And so they're limiting the amount of reaction so that they form the dihydrogen phosphate rather than phosphoric acid with 3 hydrogens or trihydrogen phosphate. But you wouldn't call it trihydrogen phosphate because it's called phosphoric acid. Now, for this here, when we do reactions in class, do it completely. Now, that doesn't mean if we alter the conditions, we can get different products. So here, they're only partially reacting the phosphate. If we completely react with phosphate, then we need 3 hydrogens for every phosphate. They only gave it 2. So they end up with dihydrogen phosphate, and it's going to have calcium dihydrogen phosphate and calcium sulfate. Well, it turns out this is what they're after. They're after this. This is the superphosphate fertilizer. Both of these are solids. You know, sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. So this is one of the few sulfates that are solids. This is a solid here. So in this reaction, I see that they're going to make 2 precipitates essentially. Actually, and then this is a solid that they're destroying. So we're making 2 solids here. Separating solids out like this can be very difficult. So they probably just leave it all mixed together and use that whole thing as fertilizer, you know, rather than separating it, which would be not so easy. Okay, so that's comment 1. I would have predicted a different product here, but obviously they know what they're doing. They're making this stuff, you know, and so they have the conditions just right to get this, you know. I guess phosphoric acid is not good. Sorry, because phosphoric acid is what we call hygroscopic. Phosphoric acid is a solid acid. Most acids aren't solid acids. Well, actually, I shouldn't say that. There are lots and lots of solid acids, you know, like salicylic acid, you know, which is an old form of aspirin, solid. Citric acid, You know, citric acid in pure form is a solid. You know, actually there are lots of solid acids. But this one, they could use it as fertilizer, but the problem is phosphoric acid is really hygroscopic, and it forms a gluey gelatin. It's just really, it's a messy stuff, you know. This is really messy, phosphoric acid. It's sticky, it gets on everything, it's hard to clean, it really sticks to glass. Whereas calcium you know, dihydrogen phosphate is probably a lot easier to work with. It stays dry. It's not as hygroscopic. This stuff just turns into a sticky, gluey mess. So that's probably why they only want partial reaction. And then this stuff is, you know, not sure. There could be other reasons as well. Well, anyway, we have this. We have how many grams? We want 0.500 tons of fertilizer. And so we have tons. We can go from tons to whatever, you know, 2,000 pounds in a ton. So we could go from tons to pounds, pounds to grams, grams to moles, moles to moles. And so we get pure calcium phosphate, moles of pure calcium phosphate to grams of pure calcium phosphate. But we're not getting pure calcium, we're getting rock. How much rock do we need? So we need the one more conversion factor, and this is what makes it an advanced problem. The one more conversion factor is this one at the end. You know, you know, they're doing kilomolar masses. I don't do kilomolar masses, I don't do millimolar masses. I would have just gone grams. So here I would have done 79.4 grams of calcium phosphate for every 100 grams of rock, and then converted it to kilograms. So they got 759 kilograms. Did everyone get that? Pretty much. Yeah, and so this is the extra step that makes this a challenge problem. You know. Well, let's go back and look at the basic problems that we work on. Yeah, okay, that'll be the quiz. Yeah, you can upload that quiz. Well, the answer's there, but you know, it's good practice. And so we'll have that as today's quiz. Okay. Again, just upload one for the group, and make sure the units, you show all the units, and that's good. You got 757. You got 757 kilograms of rock. Did we do something wrong? Okay, let's take a look at that one again. What did they get? No, it's not necessarily that you got something wrong. A 757 versus 759 is very close. Usually that's a result of some round off. So this one is exact. They're exactly 2,000 pounds in 1 ton. This is what we use. Sometimes the book uses 454. Sometimes the book uses 453.6. We always stick to the same one. We always use 453.6 grams per pound. This is exact. The situation is in the molar masses usually. And it depends on what the source of the molar masses are. And that could lead to a small difference. And so when you compare your molar mass, did you get 234.05 grams per mole for calcium dihydrogen phosphate? Did you have the same here? You got 234.052. No, when you do the molar masses, we only want 2 decimal places. Never go 3 decimal places. The only one you go 3 decimal places is for like atomic hydrogen. You know, we want to always be consistent. If we always do the same thing, then it's a lot easier to memorize. You know, for me, it's easy to memorize a lot of molar masses. Okay, so this one, I don't have calcium memorized, so I'll have to find calcium. But I do have hydrogen memorized. So we have 2 hydrogens, and that's going to be 2O2. I don't go 3 unless it's hydrogen alone. Then I go 108. And then I have how many oxygens? Well, actually, I have more than 2 hydrogens, sorry, because I got 2 times 2 is 4 hydrogens. So it's 4 hydrogens. Well, that's easy. It's 4O4 instead of 2O2. And then I have 2 phosphorus. I don't know what, I know what phosphorus is, but we can look at that. And then I have 8 oxygens, 8 oxygens. Each oxygen is 16, so 2 oxygens is 32 times, we could go 48 and then 60, whatever, 64 times 2, 128. And so this would be 128. 0.00, okay. Each one 16. So that leaves calcium and phosphorus. Now, it depends on what periodic table you use. You know, phosphorus, it depends. You'll see 2 different phosphorus masses when you look at a lot of periodic tables. So let's look at some periodic tables. This is gonna give me a mess again, because I get these ads, unfortunately. That has no molar masses. This one does have masses. So this one has phosphorus at 30.97. Okay. It's okay, 30.97. That is so sneaky. Makes it look like it's legitimate, but it's not. 39.7. And so we look, well, it looks like 39.7. And so let's go ahead and use 39.7 for that. Our book, you know, you got to compare it with our book. Depends on the date of the periodic table and how many digits they go out to and how they round it. So that can impact things there. And so again, I only go 2 decimal places because I try to keep things the same, 30.97. Calcium. Okay, let's look at calcium. 40O. Don't give me this. Okay, 4008. 4008. Let's use that. So sometimes you see small variations in the masses, and it depends on, I'm rounding these. Since I round these to 2 decimal places, that means I could get a different answer than somebody who goes more than 2 decimal places. So let's see if I get the same number they got here. It also depends this. It depends on how you round. I'm doing what I told you not to do. I'm doing intermediate round-offs. So really what I should do is I should carry all the digits. I should carry all the digits and then round at the very end, you know, to 2 decimal places here. But what I'm doing is I'm doing intermediate roundings here. I'm rounding this to 2 decimal. I'm rounding this to 2 decimal. This is 40.078. I'm rounding this to 2 decimals, 2 decimals, 2 decimals. And so that's gonna, depending on how you round things, it's gonna change your answer. And this is why we try to minimize the number of roundings we do to 1. But for molar masses, there's a huge benefit in memorizing these, memorizing certain ones, especially the big ones. Carbon, you know, 1201, you know, nitrogen, 1401, oxygen, 1601, hydrogen is 101 or 1008. You know, there's a big advantage to memorizing fluorine. Fluorine's not that common, so there's no advantage to memorizing it, but it's an easy number to memorize, 1900. You know, chlorine is 35.45. You know, I have a bunch of these memorized. Why? That way I can calculate molar masses quickly without having to look at the periodic table. And that means I can do calculations faster, you know. And so there's some advantage. Well, how did I memorize? I didn't sit there memorizing. I just use them. You use them repetitively, and then you memorize them eventually. It's like if you keep doing the same thing, you know, you ride your bike to school repetitively, eventually it becomes, you know, routine. Same thing here. I didn't sit there and say, I'm going to memorize these. I never did. You know, I never worked at memorizing them. It just happens when you use them a lot. Well, that gives you an advantage. It's not a huge time advantage, but, you know, any little bit helps, especially when, you know, there's seconds that can make a difference. So 39.7 times 2, that's wrong. It's 39.7 times 2, 6194 plus 234.06. So I got 234.06. They got 234.05. You know, that's called round off error. You know, I don't know if mine is closer or theirs is closer. We need to carry more digits to see, you know. Maybe they did some other things that are rounding. I suspect the same thing's going to happen here, and that's going to throw it off a little bit there. And so if I saw 757 versus 759 in this type of problem, you know, it's not necessarily that they're even an error. It's probably due to round off error, you know. As long as you're following the steps for rounding, you're okay. Now let's take a look at calcium dihydrogen phosphate. Let's see to more digits what it is. You can buy this stuff. Well, they got 234.05, you know, here. Do you see that? 234.05. So I suspect I'm off a bit because of my overzealous rounding. But because of my overzealous rounding means that, yeah, I have to sacrifice some accuracy for speed in a way. And sometimes that's what we do. You know, it's not perfect, but, you know, it's one of those things you could do. The other thing you could do is carry a lot of digits, but when you start carrying a lot of digits and you start punching a lot of digits in your calculator, it slows you down, you know. And this is adequate enough. Yes, we're going to be okay in this particular one. Okay, that's sigma Aldrich if we buy this. Let me see what it is on Wikipedia. Now, nomenclature, there are all kinds of funky nomenclature systems out there, you know. Monocalcium phosphate. We don't normally call it monocalcium. If you're going to go buy this stuff, you know, you buy it from a chemical company, they want to know what it's called chemically, calcium dihydrogen phosphate. So we go buy this stuff here. Oops, up here. From Sigma Aldrich is one of the largest chemical supply companies in the world. This is also very common, monobasic, you know. Let me show you something with the names. This is triprotic or triacidic. This is zero basic. H2PO4 minus. This is diprotic or diacidic. This would be monobasic. This is monoprotic or monoacidic. This would be dibasic. And phosphate is what we call tribasic base. This is tribasic base. It's a tribasic base because it can accept 3 hydrogens. That's why it's called tribasic. This is called a dibasic base because it can accept 2 hydrogens. There are 2 more hydrogens that we can add. This is called a monobasic base because it is capable of accepting one hydrogen, and this is not a base, because it can't accept any hydrogens. And so we see this monobasic word used, but there are others. These are other naming systems. Calcium dihydrogen phosphate is what we call it, but other people might call it calcium phosphate monobasic. Other people might call it calcium bis dihydrogen phosphate. Other people might call it calcium, well, the calcium dihydrogen phosphate is its common name. Calcium dihydrogen phosphate here in bold. That's the preferred name for this. Do you want to learn many different naming systems? No, you know, we'd like to learn one naming system, stick with it. Okay, but you got to realize that other people have ideas how it should be named. So if we go to Wikipedia, what do they weigh this in at? Well, actually, I didn't even have to go to the page. It's here. No, actually, it's not there. I had to go to the page. We go to Wikipedia. They get 234.05. 234.05. That seems to be the consensus mass there. So my mass is a little off, you know. My mass is off because of round-off error. You know? For example, hydrogen. If I carried it 1008, you know, if I carry more digits here and then round at the end, I would have gotten 234.05. You know, in other words. Okay. If you're getting 3 decimal places, then Francis, you're probably right there with 3 decimal places. And the same thing, Kasra. You guys are probably more. It's just me. I do it this way. I do it this way. And there's a reason I do it this way is just to make the calculations faster. Because there's always a trade-off. You know, there's a trade-off. Yeah, you got a little bit more accurate answer, right? But was it worth the time? On time tests, maybe it's not, you know. But anyway, even with, remember, uncertainty, you know, even with that uncertainty, we're both in the same range, kind of, almost. No, actually not exactly. Okay. Now you got 757. Well, let's see. And you got the same mass. Well, how big of a difference is it? 757 versus 759. And so let's take a look at how big of a difference that is. And so that's 2 parts out of 759 parts. Okay. And so 2 divided by 759. And then we're going to convert it into percent. And that gives us, they're different by 0.26%, you know, or about 0.3%. We'll call that error. There's a 0.3% error, depending on which one's right. And so something like that. Now, if it were 750 versus 759, then yeah, there's something wrong. You better go back and check it, you know. But like a 2 or 0.2 or 0.3% error is probably rounding. Rounding will give it that. Okay. Does that answer the question? Here, I made a little sacrifice to make the calculations faster. And so my answer is maybe a little off from theirs. And their answer might be a little different because, our book is overzealous about rounding. But the problem is it has multiple authors. And so it depends on who worked this problem out. There are multiple authors, so some of the authors don't like this. Some of the authors like 454, you know, rather than 453.6. So this is why we see inconsistencies here, you know, in this. The job of the editor. And so if you use 454 rather than 453.6, you're going to get a different answer here. You know, but the book does it all the time. If accuracy really matters, then carry a lot of extra digits, you know. If this is a critical calculation, then you want to be as accurate and as precise as possible. And so we carry lots of digits. But if you have a lot of questions to answer, like you know, in the homework, then you know, we do it differently. We might do it differently. what problem we're looking at before I left? Let's skip butane. Skip butane. Butane, butane is a hydrocarbon. So when we burn hydrocarbons, it burns the CO2 in water. '31, I didn't do that. Looked at dynamite. Looked at soap. Looked at this one, sodium thiosulfate, get hard water, TNT. TNT, trinitrotoluene, same type of deal. This is an oxidizer, this is a reducer in the same compound. This is how you make TNT. Okay. Pig iron, we did that. Sodium carbonate. We did that. Okay, I think 27 is where we're at right now. So we'll try to zip through these just to see, you know, the variations here. An experimenter recovers 0.521 grams of sodium sulfate from neutralization of sodium hydroxide with sulfuric acid. And so this neutralization reaction is just what I call metathesis reaction. So we had some sulfuric acid, H2SO4. It doesn't matter which one we write first. We can write the sodium hydroxide or the sulfuric acid first. But anyway, this is AB plus CD type reaction. And so we're going to have hydrogen ions with hydroxide. Hydrogen ions with hydroxide makes water, and sodium ions with sulfate. Sodium ions with sulfate makes sodium sulfate, Na2SO4. Okay, to balance this, we'll need two hydrogens with two hydroxides. So we'll need two sodium hydroxides. We're going to form two waters, hydrogen hydroxides here. Now the driving force for this is going from a stronger acid, sulfuric acid, to weaker acid, water. So stronger acid to weaker acid. That's our driving force. This sodium salts are soluble. This is actually pretty exothermic, you know. Sulfuric acid is what we call a strong acid. It's a strong acid. It's one of the 7 common strong acids that we need to memorize. Sodium hydroxide is a strong base. Now, when you mix a strong acid and a strong base, will it explode? Well, it depends on the conditions. What happens is a lot of heat is generated, and that can generate pressure. So you might have a pressure explosion, you know, or you might have like steam explosion, because, you know, a lot of heat's generated that can vaporize the liquid water into steam, cause a steam explosion. But it's not a violent, it's not like, if you mix a strong oxidizer with a strong reducer, then you're going to get an explosion. You know, that's bound to happen. But unless you can really slow the reaction down. But in this case, you know, these are a lot less violent than redox. And it's because we aren't dealing with like the, you know, the Dr. Jekyll and Mr. Hyde type deal. Oh, is it break time? Yeah, okay. All right, that's right, it's break time. So we'll take a break. Let's take a 15+ minute break here, and then I'll talk about this, continue talking about this one here, okay? All right, so break time. I'm going to pause this recording here now. So I'm listening to MedCram is a good channel for, actually it's been reviewed too, and it's been found to be a good source of information about COVID, compared to a lot of other sources that are available online. But he had a very interesting topic, and that is about school. You know, when can we resume going back to school? And one of the ideas is if we could test, if we could test students and they could test themselves daily to see, if they're positive or negative, that would be that would be great. Except the testing right now, the gold standard for the testing is a PCR test. That's an incredibly sensitive test for detecting whether you're positive or negative, but it may be too sensitive, according to some data, because there could be fragments of the virus, and those fragments, which are kind of dead and aren't going to cause any transmission, are leading to people testing positive. So there's a study in South Korea where where one family member tested positive, but none of the other family members contracted COVID-19, and that's because the person they tested positive had a real low actual viral count, and they were just this person had already recovered from COVID-19. And so well, obviously you can't test somebody and have to wait up to 9 days to get the test result. School's not going to work like that, and so there's a much less expensive test available. They're saying, and of course the price can go down even more, but I think the current cost of the test, he was saying, is only $1, maybe, or $2, and the price, if it goes, high volume, could get pretty cheap, I'm sure. And it's like just a saliva test or something, and you get the results back in 10 minutes. So you could test, you could test students every day. And if they test negative, they can go to school. If they test positive, they should stay home. But one of the complaints about this particular test was that it's only 50% accurate. But it's 50% accuracy. It's not just a 50% hit or miss. It's 50% bias towards one. And it didn't catch one type of thing. And it looks as if this test didn't catch people with high viral loads. Catch people with low viral loads, but who still tested positive in the PCR test. And so a test like that could be well worth doing. So he was pointing out a study done, and that's coming out soon. It hasn't been published just yet, but a study out coming soon from a Harvard professor there, MD, PhD, who was arguing that this would be a very effective test because it would catch people with high viral loads, and those are the people who should stay home. So this gives a way that we could go back to normal quickly, and these tests are already available, and so hopefully they get it together for the fall, and then we could do something like go back to school and go into lab. Well, tomorrow is going to be a virtual lab, but maybe in the fall we'll have real labs, And so check out that MedCram lecture. I think it was 97, 98. It's one of the latest ones. It's really interesting, and about how we can get back to going back to school. All right. Yeah, I'd like to show it right now, but I'm behind. So take a look. Maybe I'll show it. Let's see. Let's go back to this here and look at how many grams of sulfuric acid reacted. So again, when we have acid-base reactions, much less violent than redox reactions, and the reason is the oxidation states aren't changing. The oxidation states change, and the reactivity changes quite a bit. Here we're just rearranging partners. Do this partner like this partner better, or vice versa? That kind of thing. We're changing the ions partners. In Bronsted acid-base, the same thing. There's no change in oxidation state. Just changing partners. Does this proton, hydrogen ion, in acid-base, the cation's H+. What anion does H+ like better, basically. And so we have grams of sodium sulfate, this stuff, to moles of sodium sulfate to moles of sulfuric acid, moles of sulfuric acid to grams. So this is your standard, grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. So you're starting to see, this is a very common problem, and it's a very common problem, this setup here. The reaction of a dry cell battery may be represented as follows. Zinc reacts with, batteries are usually heavy. The batteries are usually very heavy because they're wet, and water weighs a lot. Water has pretty high density a gallon of water weighs 8 pounds. You know, I learned that when I was in the Boy Scouts, you know, because you can carry water. You carry a gallon of water, you're carrying 8 pounds of water. And so if a battery has a gallon of fluid in there, a solution, then it's at least 8 pounds, not more, because it's more dense. You know, sulfuric acid is pretty dense in battery. But dry cell batteries are a lot lighter. They get rid of the solution. Zinc reacts with ammonium chloride to form zinc chloride, ammonia, and hydrogen. So zinc metal, they say zinc, so I'm assuming that zinc is normally a metal. And so let's take a look at this reaction. So we got zinc, solid, the element, reacts with ammonium chloride to form zinc chloride. Ammonia and hydrogen. So what's going on here? This is a kind of interesting reaction because, you know, there are multiple properties that you can find for different compounds. In fact, you know, if I asked you, hey, what are the chemical properties of HCl? There are 3 chemical properties of HCl. 1, it's a strong acid. I know that. 2, it's an oxidizer. Why is it an oxidizer? Because of H+. H+ is an oxidizing agent. 3, it's a metathesis agent. It precipitates, you know, because chloride ion likes certain cations, silver, lead, and mercury. So HCl reacts with silver, lead, and mercury. So it's a precipitating agent for silver, lead, and mercury because we'll form silver chloride precipitate, lead 2 chloride precipitate, mercury 1 chloride precipitate. And so when we look at a chemical like this, any chemical, I look, you know, what are its redox properties? What are its metathesis properties? What are its acid-base properties? And strong acids love lots of bases. And so ammonium chloride, you know, ammonium chloride is the same thing, you know, what are the properties? And so when I talked about ammonium, you know, I was talking about ammonium being a good fuel, you know, you could burn it. But interestingly, ammonium is also an acid, and acids can attack metals like zinc and oxidize them. And so this is kind of a weird reaction because you think, hey, wait a minute, isn't this an ABX? If this is ABX, then it's single replacement, right? But it doesn't fit that pattern here. It doesn't fit the ABX, but this is a redox, or it could be thought of as a redox reaction in which ammonium's acting as acid, oxidizing the zinc to Zn2+ here. And so indeed, that's what's happening because zinc starts off at 0 here. Now, ammonium, chlorides, nothing's happening to chloride. You know, chloride stays -1 here, stays -1 here. The zinc goes from Zn0 to Zn2+, so this goes +2 here. So zinc's losing electrons. Who's it losing electrons to? Well, it's losing electrons to ammonium, but this is very, very tricky here. It's very tricky because why would ammonium want it? Because ammonium is electron rich. You got -3. Well, in this case, it's the hydrogen in ammonium. The hydrogen, ammonium, one of the other properties of this is it's an acid. It's an acid, it's because of the H+ here. You know, we've got the charge here. And so acids, we already know H+ is an oxidizer. 2H+ is like 2 electrons to form hydrogen gas. So that's what's happening here. H+ in ammonium is taking electrons to form hydrogen gas over here. And we're left with ammonia. And so it's that extra hydrogen here. So this is a very tricky reaction to see. But we got ammonium here. Ammonium's -3 on the nitrogen, but +1. And so, you know, when we're looking at chemical properties, you know, a lot of things will behave, you know, they'll have multiple properties. And the way they react depends on what you react them with, you know. So if we react ammonium with an oxidizer, you know, Don't mix ammonium with bleach either. They say don't mix ammonia with bleach. So don't mix ammonia with bleach. Bleach is an oxidizer. Don't mix ammonium with bleach too. That's an oxidizer. But then ammonia, this is a base, but this is an acid, you know? And so redox wise, like if you mix them with bleach, they behave very similarly because this is -3, this is -3, but you know, acid base wise, they're totally different animals because this is an acid here. This is a base here. So totally different in terms of reactivities. But so this kind of interesting reaction that happens here, you might have been able to tell, you know. In fact, ammonium chloride, I would have looked at it maybe like the zinc solid reacting with ammonium, and ammonium being an acid, you could attack it. And we could look at it in different ways as well. You know, ammonium can produce something called hydronium in water, and so when ammonium can also react with water. And when ammonium reacts with water, it produces ammonia and hydronium, H3O+. Hydronium is on your acids list, you know, and hydronium is only when we have acids react with water. That's how we form hydronium. We don't buy hydronium, but, you know, when acid's in water, it's already there. And so this hydronium is AKA H+, AQ. These two things are the same thing. And so I could go, instead of 2H+ here, I could go 2 hydroniums. 2 hydroniums plus 2 electrons yields hydrogen gas plus 2 waters. Same thing. You learn more about this in Chem 1B, but it turns out that protons are extremely unstable in water. Protons are super reactive. And so if we ever have a proton in water, it immediately reacts with water as a proton. The reason why protons are super reactive is not because of the +1 charge, it's because of its volume. Its volume is extremely tiny. And so that +1 charge is concentrated in an extremely tiny volume, making it super reactive. This is the same thing, you know, this is super reactive, just like alpha particles. Alpha particles are super reactive because alpha particles are helium nuclei, essentially, because helium normally has 2 electrons. If you knock off the 2 electrons, then all you're left with is 2 protons and 2 neutrons in a nucleus. And so that makes this extremely reactive, you know, 2 protons and 2 neutrons in the nucleus. This is why alpha radiation is so damaging, because it's so reactive. You have a +2 now concentrated into a tiny, tiny nucleus, compared to +1 concentrated in a tiny, tiny nucleus here for the proton. So alpha particles are much more reactive than protons, and protons are very reactive, so they're going to react with water to form hydronium. This is why we see hydronium. And so I'll talk more about hydronium when we get to the acids chapter, but for now. So that's the other way of visualizing this. The other way of visualizing this reaction is the ammonium will react with water to form hydronium, aka H+. The H+ oxidizes zinc to Zn2+ and hydrogen. And then when ammonium reacts with water to form hydronium, it also loses the hydrogen, the proton, to make ammonia. And so it's a little bit more complex, but you know, you can better recognize these if you see a lot. You know, the more reactions you see, the more you can see, you know, this is just a twist of your basic reaction, redox reaction, that kind of stuff. So this is an advantage. If you only study one type of thing, you know, and never look at other things, then it's harder to see these kinds of things, you know. And so, so this is why I like what they call, I like the volume versus, you know, some people argue with me, of course. They say, you know, it's better to get quality than volume. Me, I think volume is better, you know, initially, and then you can work on quality. Volume meaning do lots of problems. So the more homework problems, the better. Well, anyway, pretty soon these get old, like grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. Pretty soon they get old. You know, it's like, you know, when you first start riding a bicycle, it's pretty challenging, but, you know, pretty soon it gets, you know, easy. That's kind of what happens. Yeah. We just need the balanced chemical equation. The function of sodium thiosulfate, so there's sodium thiosulfate again, in photographic developing is to remove excess silver bromide by the reaction here. So let's take a look at this reaction here. This is kind of a weird reaction that's going on here. So this one, to me, I would have predicted different products, because I would have looked at this and said that, hey, this is an AB plus CD. So A is the sodium ion, B is thiosulfate ion, C is silver ion, D is bromide. So I would have predicted this should form sodium bromide and silver thiosulfate. Silver is +1, thiosulfate's -2, so we'll need 2 silvers for every thiosulfate, like that. But this one forms something very weird here. And, you know, this is why we still need, this is why chemistry is two-pronged. You know, when we look at chemistry, chemistry is a mix, you know, of course, you know, we want theory, but there's also, you know, observation, you know, or memorization, observation. You know, theory versus experimental observation. Yeah. They go hand in hand. The reason is theory is too complex sometimes. So it depends on the conditions you do this with. Now, this is a very strange species. This kind of species is talked about in Chem 1B. This is a weird, you know, what's going on here? Well, there are two ways of kind of thinking about this. One way is this could be a mixed cation salt. You know, mixed cation salt. Do you remember where we saw mixed cation salt before? I did a couple of them. Nobody remembers? One of them I did was this one here, I think. What was this one? You know, where we mix potassium and sodium, potassium sodium phosphate, but this is 2 sodium, so potassium disodium phosphate, something like that. So this could be two different atoms. We have 3 sodiums at +1, 1 silver at +1, and that's going to give us a total positive charge. Something like this has got to be, I think, a precipitate, you know. And so why would this form? Well, it must form some kind of crystal, and this comes from probably observation. You know, this just so happened to form. That's it. Yeah. The other thing we're going to see, or in Chem 1B, then we'd recognize this. This is a special species, AGS203 2. 3 minus, you know, this is called a complex. This might not be a solid. Could be that we're just complexing the silver like that. And so, well, anyway, it's removing silver bromide. Silver bromide's a solid. And because chlorides, bromides, and iodides are insoluble. And so what's happening here is the thiosulfate is attacking the silver ion and complexing it like that. This is a Lewis acid base. So anyway, so you might not have predicted that because this just looks like an AB plus CD, double replacement. But depending on the conditions and how it's done, it could change what products are made. But still, there's a utility there and be able to predict things. And the more types of reactions we see, like these complexes and Lewis acid base, the better. But anyway, this is just going to be a grams of A to moles of A type deal. Grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. That's it. Oops, I didn't do one other thing here. They added one more thing. They call the ideal. I call this the theoretical yield. This is how many grams of sodium bromide in theory based on the stoichiometry here. But they only got 2.61. You see it says produces 2.61. Produces means that they must have gotten this experimentally. So they only recovered 2.61 out of the 2.66. So they lost 0.05 grams somewhere. And so when we calculate the percent yield, we take the actual yield, what they actually got in the experiment, divided by the theoretical yield. So this is AY over TY times 100%. So they get 98. So they lost 1.9% of the sodium bromide was lost or never formed. It's like the popcorn. Remember the popcorn? So now we're doing something different. We're doing not just our standard calculation, which gives us our theoretical yield, but now we're adding some experimental data there to show what they actually got. Butane, skip that. Calcium cyanamide is a common fertilizer. When mixed with water in the soil, it reacts to produce calcium carbonate and ammonia. The ammonia is the fertilizer part. So the cyanamide, this looks like cyanide, but it's not. It's CN with two nitrogens, not two cyanides, and water. And so there's some redox reaction happening here to form some ammonia, I think. Or no, maybe there's no redox reaction. Maybe this is acid base. Let's take a look at this in more detail here. So I'm looking at this in more detail. Calcium gets assigned first, that's +2. And then nitrogen at -3. So we got -6, +2 is -4, this is +4. Okay. Hydrogen gets assigned first at +1, and oxygen's at -2. Here, calcium gets assigned first at +2, oxygen next at -2. So -6 +2 is -4, this is +4. And hydrogen gets assigned first at +1, nitrogen's -3. So when we look at it, nothing changed. And so this is an example of a Lewis acid-base reaction, Lewis acid-base, because it certainly isn't metathesis. We aren't, swapping partners for the ions. This is Lewis acid-base. It's not Bronsted acid-base either. Here, that's Lewis acid-base. We didn't really talk about Lewis acid-base. Lewis acid-base reaction is a bit more complicated. Excuse me. So how much ammonia can be obtained? So we're going to start off with 7.25 grams of calcium cyanamide, this stuff here, in a laboratory in which the percentage yield. So they already know, sometimes you do this reaction over and over and you always lose a little bit and you always lose a consistent amount. So what they're doing is they're predicting they're going to lose, they're going to lose 7.2%. And they're only going to recover 92.8%. And so they're asking how much is going to form from that. So let's just take a look at how they did that here. So grams to moles, moles to moles, moles to grams. Now this, if we stop here, this gives you the theoretical yield of ammonia, ammonia being the fertilizer. But we're going to lose a little bit. How much are we going to lose? We're going to lose 7.2%. That means we're going to recover 92.8% of it. And so for every 100 grams that in theory we make, we're only going to get 92.8 of those grams in actuality. And so rather than making the full amount, the full amount would be, the full amount would be, let's say 7.25 divided by 80.11 times 2 times 17.03. They should have gotten 3.08 grams. 3.08 grams. If they didn't lose anything, the theoretical yield is 3.08 grams here. But they're anticipating they're going to lose a little bit, and so they only got 2.86 grams. If we take 2.86 over 3.08 times 100, we should get 92.8%. And so this is just, we're going to lose some, so let's predict how much we'll actually get. That's based on how accurate this is, because sometimes we lose more than this, sometimes we lose less than this. And so maybe they're just saying this is the average loss in this reaction. Because how can you predict how much you're going to lose? That's not something that's so easy to predict. If it were easy to predict, then maybe what you should do is you should just work at trying not to lose any. The Haber process for making ammonia. Ammonia is very important for fertilizers. So the problem is ammonia is a gas. The Haber process for making ammonia from nitrogen in the air is given by, so we can take nitrogen. In this case, what's happening here? Well, nitrogen is going to oxidize the hydrogen. In this case, this is a redox reaction. So nitrogen is actually the oxidizer now. And it's going to oxidize the hydrogen. So nitrogen starts off at 0, hydrogen's at 0, and then we'll go to ammonia. Hydrogen's +1, nitrogen's -3. So nitrogen's oxidizing the hydrogen. In other words, we're burning hydrogen with nitrogen, but nitrogen is not a very good oxidizer. And so this Haber process doesn't really work so well. And so the Haber process, what they did was they tweaked the conditions. They tweak the conditions in terms of temperature and pressure, and they figured out where they can get the most ammonia. It turns out this is not a very good reaction. This is an excellent yield. 88.8% is an excellent yield for this because it just doesn't work so well. Nitrogen's not that reactive. Not like oxygen. If this were oxygen and hydrogen, forget it. That would be an explosion. But with nitrogen and hydrogen, it's a tough reaction to do. But under the optimum conditions of pressure and temperature, they were able to get this high of a yield. It's pretty impressive. And so this is a similar problem to the last one. Calculate the mass of hydrogen that must be supplied to make. Okay, now we have to be very careful here. When we do percent yields, take a look. We have to be very careful because in one direction, we use it as a regular percentage. In the opposite direction, we have to flip it upside down. And so when we look at this last problem, this is just, 92.8 parts out of 100. That's a normal percentage, right? Take a look at what we have to do here. What we have to do here is a bit different because of this. We're starting off with this. And so it's like this. This problem, this is my analogy for this problem. Let's say you need 100 cookies. Let's say you need 100 cookies for a party. And so, in actuality, you need 100 cookies for a party. We labeled that actual yield. You better have an actual yield of 100 cookies for this party. But let's say when you bake these cookies, each time you bake these cookies, you only get for every 95 cookies actual yield, you have to bake 100 because you like to eat 5 of them. And so that would be your theoretical yield. And so how many cookies should you bake in order to have 100? Well, you're going to have to bake more than 100 because if you're going to eat 5 out of 100, and so let's say you lose 5% of your cookies through eating them. And so how many does that mean you better bake? Oh, that's 100 times 100 divided by 95. And so you better bake 105.2 so that you can eat 5% of them, you know, or 106 cookies or something like that. And so do you see this is flipped upside down? It's flipped upside down because now we're looking at how much product we want here to make. And so this is a bit different. So we have to label, you know, this 5.00 kilograms, 5.00 times 10 squared, 500 kilograms of ammonia, NH3. Now, this is not the theoretical, this is the actual yield. So I do an additional label. When I'm doing percent yield problems, I label it actual or theoretical, because that's going to dictate if I flip the percentage upside down or if I leave it right side up, 95 out of 100. All right, so when I look at the percent yield here, this is 88.8 actual over 100 theoretical. And so that's what we're going to have here, actual yield of product. And so this is actual yield of grams of ammonia versus theoretical. So for every 100 grams of ammonia that I set out to make, I'm only going to recover 88.8 grams actually. And so here I go from kilograms to grams. And then once I have grams of ammonia actual yield, then I'm going to use this. But I have to flip it upside down because I have 88.8 grams of ammonia actual yield for every 100 grams of ammonia theoretical yield. And so, so once I get that, then I can go into my stoichiometry. I'll just go grams of A to grams of B. Grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. So do you see how it's inverted here? And you got to label it. So I call this AY, actual yield. I didn't call it ideal, I call it theoretical yield, TY here. And then we can just go from here into it. And they're using these kilomolar masses and kilomole conversions, which I don't do. I told you. And so note the difference here. The percentage here versus the percentage here and why they're different. Calculate the percentage yield in the photosynthesis reaction by which carbon dioxide is converted to sugar. If 7.03 grams of carbon dioxide yields 3.92 grams of sugar. The equation is this. So this is photosynthesis, CO2 and water. The plants use this and convert it to sugar and oxygen. And so the 3.92 grams here, that's actual yield, you know. This is actual yield. And so what we're going to do is we're going to take our 7.03 grams of CO2 and figure out what the theoretical yield of sugar is. This is glucose, by the way. And so we want to figure out what the theoretical yield of the sugar is. And that way we can figure out the percent yield, because the percent yield is given by the equation this. It's the actual yield divided by the theoretical yield times 100%. And so we're just going to use stoichiometry to figure out what the stoichiometric amount of sugar should have been. And so how much sugar should we have made from 7.03 grams of carbon dioxide? So 7.03 grams to moles CO2. So grams of CO2 to moles of CO2. Moles of CO2 to moles of sugar to grams of sugar. It should have made 4.8. If we had 7.03 grams of CO2, we should have gotten 4.80 grams of sugar. That's a theoretical yield. And so we just take the actual yield, 3.92, divided by the theoretical yield times 100% gives us 81.7% yield. So, you know, some of the CO2 was lost, or some of the CO2 wasn't converted. It wasn't, or, you know, the efficiency of the reaction wasn't perfect. So 81.7%. Ethyl acetate is manufactured by the reaction between acetic acid and ethanol. So if we take acetic acid and ethanol, we can make ethyl acetate. Ethyl acetate smells pretty good. A lot of these, you know, have nice smells to them versus the awful smells of thiols. And a lot of them are responsible for fruit, the nice smells of fruits. How much acetic acid must be used to get 65.2 kilograms of ethyl acetate if the percentage yield is 69.1%? And so they need to get this much. This is for the party. And so maybe they're trying to do it. What does ethyl acetate smell like? I'm just kind of curious. Ethyl acetate smell. Pears. It smelled like pears, maybe. No, maybe not. Maybe it's not so good. Sweet smell. Similar to pear drops. Okay, sweet smell. Why does ethyl acetate smell fruity? No, anyway, it's got a pleasant fruity smell. Okay. So this is how much they want for their party. Maybe they want sweet, fruity smelling ethyl acetate for the party. They need 62.5 kilograms. So this is going to be the actual yield. And so we need to get this much. And so we got to figure out, well, if we get that much actual, how much do we need to make theoretical? So we go 62.5 kilograms of ethyl acetate. Ethyl acetate, I'm just going to abbreviate ETAC. You know, ET for ethyl, AC for acetate, ETAC. And then we'll just convert that to grams because I'm not a kilogram type in the core section of my thing. And so we'll just do that, kilogram, 1,000 grams. And then I like my percentages in grams, you know, usually. But it doesn't matter. You could do percentages in kilograms. I'm sure your book is going to do it in kilograms. And so 69.1. And so we have to label this. This is what we actually want. And so this is going to be 69.1 grams of ethyl acetate, ETAC, actual yield, AY, over every 100 grams of ETAC, ethyl acetate, theoretical yield. And so this is, in theory, if I want 62.5 grams, then how much do I have to make in theory, or plan to make in theory? So it's going to be 62.5 kilograms times 1,000 times 100 divided by 69.1. I have to make 90,448 grams, or 90 kilograms. And so if I want 62.5 kilograms, I better be prepared to make about 90.5 kilograms because I'm going to lose a bunch. It's got a pretty low percent yield. But we carry on, you know, then it turns into standard stoichiometry planning. And so again, here, kilograms to, oh, they're converting, they're using the percent. This is a percent yield here. They're keeping everything in kilograms. Okay. Ammonia can be formed from a combination reaction. Ammonia, well, this is the Haber reaction, nitrogen reacting with hydrogen, the elements. A small fraction of unreacted mixture of elements is illustrated in the diagram. White spheres represent hydrogens, blue spheres represent nitrogen. The temperature is such that all species are gases. Yeah. Okay. Write the balance equation for the reaction. Well, this is nitrogen and hydrogen yields ammonia. Nitrogen and hydrogen yields ammonia, so we just balance it. Here, again, the formatting is weird to me. There should be no space. It should just be N2 gas, no space. And then 3H2. I do no spaces. 3H2 gas yields 2NH3 gas. Which of the following correctly represents the product mixture? Okay. This is a limiting reagent problem. We talked about it. So for every nitrogen, we need 3 hydrogens. So how many nitrogens do we have? 1, 2, 3, 4, 5, 6. So if we have 6 nitrogens, we're going to need 3 times 18 hydrogens. So let's see how many hydrogens we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We don't have enough hydrogens. And so we have too many nitrogens, not enough hydrogens. So we call hydrogen the limiting reactant. The nitrogen is excess reactant. It's got to be this. Here. Let's see how many. We had 12 hydrogens, so 3, 6, 9. Did we have 12 hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, we needed 18. So 12 hydrogens, we should make how many ammonias? So 2/3 that amount. So we have 12. This is the smaller amount method. You know, if we have 12 H2s, then there should be 2 ammonias molecules for every 3 H2 molecules. These are molecules. And so 12 divided by 3 is 4, times 2 is 8. So we should form 8 ammonias. Did this form 8 ammonias? Which of these formed 8 ammonias? 1, 2, 3, 4, 5, 6, 7, 8. This one did. Okay, and then we'll have, okay, 2, 4, 6, 8, and then we'll have 2 nitrogens left over. Yeah. And so it's got to be this one here. We're going to have 2 nitrogens left over. Because 8, you can see it here. There are different ways we could do it, a bunch of different ways. But if we have 8 ammonias, then how many hydrogens did we use? Well, half the amount. So we used 4 of the nitrogens. Well, how many nitrogens do we start with? We started with 6, so 2 are going to be left over. So that's what we have. Which species is limiting reactant? Hydrogen is limiting reactant. Here. It's a smaller amount. (43) An experiment is conducted in which varying amounts of solid iron are added to a fixed volume of liquid bromine. The product of the reaction is a single compound, which can be separated from the product mixture and weighed. The graph shows the relationship between the mass of iron in each trial versus the mass of product compound. Explain why the graph has a positive slope for low mass of iron and a 0 slope for the mass of iron. It becomes larger. And so what's happening here is the iron is, there's excess bromine here. And so the iron reacts with bromine. And as the iron reacts with bromine, we form more and more product. But pretty soon, there's no more bromine left. When there's no more bromine left and we keep adding iron, nothing happens because there's no more bromine. And so in this part of the curve here, you know, iron's a limiting reagent. We have plenty of bromine, not enough iron. So all the iron's reacting. When we hit here, it's stoichiometric, you know. Now we've used up all the iron. and all the bromine. Now, if we keep adding iron, then we're going to have excess iron. But there's no more bromine, and therefore there's no more reaction. So that's what's going on there. Even though this one's not a blue one, I want to talk about this one here. This is zinc and hydrochloric acid. So here we see, you see that there's chunks of zinc there, and the balloon's filled. And so what this is the reaction's over. They're telling us the reaction's over. And so there's no more hydrochloric acid left here to react with the zinc. The zinc is in excess. So I can keep adding more and more zinc. Nothing's going to happen because there's no more hydrochloric acid. No more HCl, aqueous. It's all reacted. And this is hydrogen gas in here. The reaction is zinc plus 2 HCl's. This is single replacement. Yields zinc chloride, redox, plus hydrogen gas. And so even if we dump in a whole bunch of more zinc in there, there's no HCl left, so nothing's going to happen. The balloon is maxed out, basically. Here, this is stoichiometric. There's no zinc left here, and there's no more hydrochloric acid. We know there's no more hydrochloric acid, but the balloon's maxed out. Here. So this is stoichiometric. This is excess zinc. This is stoichiometric, just the right amounts of everything. So there's no more zinc, there's no more hydrochloric. And so we call it stoichiometric. This one, there's no more zinc, but there's hydrochloric acid left. I know there's hydrochloric acid left because we haven't maxed out in the hydrogen gas. Hydrochloric acid is going to make the hydrogen gas. And so this must mean there's excess hydrochloric acid. We just don't have enough zinc to create it. And so no more zinc. No more zinc. So zinc is the limiting reagent here. Hydrochloric acid is the limiting reagent here, and this is stoichiometric here. This is a pretty interesting visual. A solution containing 1.63 grams of barium chloride is added to a solution containing 2.40 grams of sodium chromate. Find the mass in grams of barium chromate that can precipitate. So whenever we're giving two reagents, like barium chloride, and so we know how much barium chloride we have 1.63 grams of that. Whenever we're given two or more amounts here, then it's always limiting reagent. And so this is 1.63 grams of barium chloride. What's the reaction here? The reaction is barium chloride, Ba is 2 plus, chloride's 1 minus, so we'll need BaCl2 plus sodium chromate, which is going to be Na2CrO4. And this is metathesis. So barium is paired with chromate now. Barium, chromate. Chromates are all insoluble, except for group 1 and ammonium. And sodium is going to be paired with chloride. We'll get sodium chloride. We balance this. We'll need two NaCl's here. This is going to be aqueous. And so this is our precipitate. Driving force is precipitation. This is going to be aqueous. This is going to be aqueous here. So the problem here is if they only gave us barium chloride, then this is standard stoichiometry. We assume we have plenty of sodium chromate, but they give us both. They tell us how much barium chloride, 1.63 grams, and they tell us how much sodium chromate, 2.40 grams. And this is not necessarily stoichiometric. If this is stoichiometric, then, then they're just the right amounts. But we don't know which one is just, we don't know if we have too much barium chloride or if we have too much sodium chromate. And so we use the smaller amount method. I don't know if they use it here. They present two methods, comparison of moles method and smaller amount. I don't do comparison of moles method. Why? It's good to do, the more variety you see, the better, but it's not necessary. It's simple though. I use the smaller amount method. That's what the smaller amount method is. And so the smaller amount method is I do the yield from barium chloride, 1.63 grams of barium chloride. And so the first part is determine the yield from 1.63 grams of barium chloride. And so if I figure out the product yield, I should get 1.98 grams of barium chromate. And then I figure out the yield from the other reactant. The other reactant would be 2.40 grams of sodium chromate. And it yields 3.75 grams. And then I compare the two. Well, it looks as if sodium chromate's in excess. The reason is because it could potentially form 3.75, but it won't, because the max amount I can form from barium chloride is 1.98. Once I form this, then I have no more barium chloride left over. And so what that means is the smaller amount is the amount I'm going to make. This is my theoretical yield. And so the smaller amount equals the theoretical yield. There's no way we're going to make that much here, as we don't have enough barium chloride here. And this is going to be called the limiting reagent. 1.63 grams of barium chloride is the limiting reagent, LR. This is going to be called the excess reagent. Excess reagent. And so the theoretical yield of barium chromate is 1.98 grams. We can't make more than that. So barium chloride is the limiting reagent. The yield is a smaller amount, 1.98 grams of barium chromate. Now this final calculation is how much excess reagent remains unused. You know, how much did we waste essentially? So we started off with 2.40 grams. Did we really need? No, we didn't need 2.40 grams. And so this last calculation is the amount of excess reagent remaining unused. The amount of excess reagent unused. And so this is how we do it. We figure out how much we had at the beginning, and then we figure out how much we used. This is used by the limiting reagent, used by the LR, limiting reagent. How do you figure out how much you use from the limiting reagent? Well, we know what the limiting reagent is. Limiting reagent is 1.98 grams, 1.63 grams barium chloride here. This is the limiting reagent. So we start off with the limiting reagent here, and then we figure out how much sodium chromate is used. And so 1.27 grams of sodium chromate is going to be used by the LR, limiting reagent. And so that 1.27 grams is this here. And so the way we calculate how much of the sodium chromate is used by the limiting reagent is we start off with the limiting reagent, we go grams of limiting reagent to moles, then moles of limiting reagent to moles of excess reagent or sodium chromate, and then moles of sodium chromate to grams. And this is, 1.27 grams is the amount required theoretically or stoichiometrically for 1.63 grams. We actually started with 2.40 grams here. So 2.40 minus 1.27 gives us 1.13. So 1.13 grams of sodium chromate is kind of wasted. It's unused. It's left unused. So this is an additional calculation that's common. That is, how much of the excess reactant remains unreacted, unused. And so very common calculation here, this second step. And so this first term here is given. The second term we calculate using stoichiometry, and that stoichiometry calculation is up here. Okay, there's a break time. keep track. I think, oh yeah, that's right. It is break time. It's supposed to end the break, the last break. All right, let's do break time here. I'll probably stop the recording this time. Then we'll do break time and then we'll meet back here in 15, all right?